This is the fifth session of thermodynamics with P. Mohammed. I talked about the second law of thermodynamics as three descriptions. One was Kelvin's statement, the other Clausius, and the other Carnot. In this session, I want to use Carnot's statement to enter entropy and add another description of the second law. Actually, we had three descriptions, and I want to step by step build another description for the second law. For a heat machine, we had if a heat engine had two properties, it was named a Carnot machine. One was reversibility, and the other was that the machine works between two constant temperatures. Actually takes Q1 or QH from a hot place with θ temperature and gives Q2 to cold or actually with θ2 temperature. Okay, now we had efficiency, which was W divided by Q1, and what is W? W is Q1 minus Q2 divided by Q1, and this will become Q1 minus Q2 divided by Q1. Okay, imagine a machine has the second property, which means it works between two constant temperatures. With this property, actually we don't need reversibility, just a machine which works between two constant temperatures. I want to say that its efficiency is a function of two temperatures. Actually, we can talk about this, but if you have problem with this actually statement, I can say that imagine a machine has this property, not all of machines. But after that, we will accept that this is true for all machines that work between θ1 and θ2. Actually, when we said Carnot's statement, we didn't talk about what the engine is. Actually, the work is electrical, magnetic, or mechanical. We said all of machines that have these properties have this, that their efficiency is smaller or equal to efficiency of Carnot machine. Okay, so nothing was important, just these two properties. Now, if is not reversible, also it has this actually property that its efficiency is a function of the two temperatures. Okay, now when eta is a function of two temperatures, so this fraction is that function, another function too. So Q2 divided by Q1 is a function, actually another function of two temperatures. I use this here and find this function. Let's imagine that there are three places, θ1, θ2, and θ3. Here is an engine and here is another engine. W1, this is Q1, this is Q2, and the same Q2 enters the second machine, and this is Q3 and this W2. Okay, the same heat that exits from the first machine enters the second machine. Here, for this machine, we have Q2 divided by Q1 is that function of theta 2 and theta 1, theta 1 and theta 2. And here we have Q3 divided by Q2. Q2 is that function of theta 2 and theta 3. We have these two. And now, when this heat is the same as this heat, we can forget about the second place and imagine that that's this two places, and another, actually a new heat machine that is some of these machines, and it has a W1 plus W2. It takes a Q1 and gives a Q3, and for this machine we have Q3 divided by Q1 is a function of two temperatures, which is the function of theta 1 and theta 3. Am I right? These are simple till now. Now multiply both sides of these two, and you will have, if you multiply this side, we have Q2 is cancelled, and we have Q3 divided by Q1 is multiple of this side, which is the function of theta 1 and theta 2 multiplied by the function of theta 2 and theta 3. Okay, and we still have this one, which Q3 divided by Q1 is the function of theta 1 and theta 3. Look here, these are equal, so this side, the right hand side of two relations are equal too, so the function of theta 1 and theta 2 multiplied by the function of theta 2 and theta 3 will become the function of theta 1 and theta 3. So when you multiply these two functions, theta 1, theta 2, theta 2, theta 3, theta 2 must be cancelled. So now I can define the function as this: a function of theta 2, okay, divided by a function of theta 1. If you use this function for f prime, this is held. Okay, so we have a T here, I name it T eta. This is a temperature that we defined from Kalman's statement, which is equivalent to the second law of thermodynamics. So theta of eta is a temperature that is a function of theta, and theta is from every thermometer. Actually, it's not important that how we measure this temperature, and I will show that this temperature theta of eta is the same as the temperature that we have in this relation, the ideal gas law. This T is this T, but for now that's not necessary to prove it. To prove this, consider a temperature T. Here till the end, by T I don't mean this T, I mean theta of T of eta, and after some videos we will see that actually these are the same. So now Q2 divided by Q1, which was this function, will become T2 divided by T1, which T is a function of temperature. Actually, it can be a square of theta or a logarithm of it. It is a function of temperature. Okay, so eta will become 1 minus Q2 divided by Q1, which is 1 minus T2 divided by T1. This efficiency is for machines that work between theta 1 and theta 2, actually constant temperatures. It's not necessary to have machine. So now let's talk just about machines that work between constant temperatures. When I say a heat engine or a heat machine, I just mean a machine that works between two constant temperatures, unless I actually tell you that I mean something else. Okay, and it is a Carnot machine if the processes can be reversed. Now, Carnot's statement was this: eta of every machine is smaller or equal to eta of Carnot. Now, from Carnot's statement we had this. Okay, now this is a Carnot machine, this is reversible and works between two constant temperatures, and this works between two constant temperatures but is not necessarily reversible. Imagine that is irreversible. This should be smaller. The equality is for when the machine is a Carnot machine. So if a machine is irreversible, so it is not a Carnot machine, and its efficiency is smaller than eta of C. So eta of C was 1 minus T2 divided by T1, and if we use this for irreversible machine 2, it will be actually equal. So here we should add the first property 2 for this actually formula. Okay, so this formula is for two constant temperatures and also for reversibility, and actually it is for Carnot machine. Okay, but the formula that eta is 1 minus Q2 divided by Q1 is for every machine. Okay, so at the first I told you we need just the second property, but here we said that if we don't use the first property, Carnot's statement will have problems. So now imagine we have an irreversible machine and a Carnot machine. We have this inequality. This is efficiency of Carnot machine. This is efficiency of irreversible machine, which both of them work between two constant temperatures. So I can actually, these Q's are irreversible. Okay, and I can write it as this: T2 divided by T1 is smaller than Q2 irreversible divided by Q1 irreversible, and and these Q actually are amount of Q's and they are positive. Okay, so I can move them to the other side of inequality. So Q1 irreversible divided by T1 is smaller than Q2 irreversible divided by T2. These are results of Cardinal statement, okay? And so Q1 irreversible divided by T1 minus Q2 irreversible divided by T2 is smaller than 0, it's negative. Now Q2 is the amount, but let's actually consider all of Q's with signs. Actually Q can be positive or negative. So now if this is a system, every Q that enters the system is positive and every Q that exits the system is negative. Okay, so we have this. Actually we have Q divided by T1 as a quantity. You will see that this is somehow entropy, but not exactly this. And we have this, okay? And if this was reversible, this would be equal sign, and all of these would equal, and this would be equal sign. And so I have this more general relation as a result of Cardinal statement that Q1 divided by T1 plus Q2 divided by T2 is smaller or equal to 0. And equality is for when Q's are reversible. The machine is reversible, the processes are reversible. Okay, a machine actually, let's have this and look the diagram of a machine. Look, I told you that I talk about machines that work between two constant temperatures. What is the diagram of constant temperature? Actually, isothermal. I told you that from this PV equal RT, if T is constant, so we have PV equal constant, and this is a curve for PV constant, and this is a T1 for example, and this is a T2. And a machine, if you look at a machine, it takes a Q1 in constant temperature and gives some work, and gives Q2 in constant temperatures. So exchange of heat is done is constant temperature. So here, for example, a machine begins from here, and in this process takes some work and somehow goes in the other temperature, and again goes here, and in this path gives some amount of heat and comes back in the beginning temperature. And these curves, which are actually going from one temperature to another, these are adiabatic processes. So a machine, actually I didn't draw it well. This is PV. This is a cycle of a heat machine. These are constant T and these are adiabatic. So in adiabatic, Q is 0. Let's have the first law here, dq minus dw. In constant T processes which we have exchange of heat, du is 0, and so all of dq will become dw. So producing of work is done in these processes, and here which the machine goes from one temperature to the other, dq is 0, because in adiabatic, actually an adiabatic process is defined to don't have a heat exchange, so the W is equal to the U. Okay, now when I say that this is a result of Carnot machine, I can look at both the result and the diagram. Here in this process, constant temperature, we have an exchange of Q2. So in this process, in this isothermal, I have a Q2 divided by T2, and here I have a Q1 divided by T1. Now I can have two Carnot machine that work one after another. It will be like this. This is Q3 divided by T3, Q2 divided by T2, Q1 divided by T1. Okay, and now I have the inequality here too. For this Carnot machine I have it, and for this I have it too. So in general I can write that result like this: Qi divided by Ti is smaller than or equal to 0. Okay, and now this part is very interesting. Imagine that we have a cycle, an orbital cycle, that a system paths this cycle, and we can actually divide it to about, for example, 1000 isothermal processes, and each of these are a differential Carnot cycle. Okay, and so this sigma will become an integral. If each cycle has a dq divided by t is in the whole cycle is smaller or equal to 0. So actually the results that we have from the Carnot statement is become like this, and we have this. Okay, and now I want to name this differential amount as ds, which is entropy. And when integral of this is smaller, so ds, actually delta s, is smaller than 0 or equal to 0. Delta s is this integral. Actually delta s is integral of dq divided by t in a cycle. And now I have defined entropy, And the second law has a fourth description. One was Kelvin, two was Clausius, three was Carnot, and now it has entropy, and entropy from the second law says that entropy never can increase. And we should talk about this law, that why entropy can't increase. Actually, we can have a system that takes Q or gives Q to the other, and it can have increasing in entropy, but this is about adiabatic processes, which we will talk more in the next session, which is about entropy, especially about entropy. So we have reached to what is entropy from the second law. I hope you enjoyed this lesson with these videos. I am P. Mohammed. Till next video, good luck.